Today we're talking about implicit differentiation. And before we can talk about what implicit differentiation is, we have to talk about what implicit is versus explicit. It's pretty straightforward. Okay? We're going to start with explicit. Explicit is everything we've been doing so far. You have already seen explicitly stated equations of curves and implicitly stated equations of curves. We just didn't call it that. But you've seen them before. But we've only been differentiating so far explicitly stated equations of curves and lines. Explicit is something like this. Come on. Okay, there's three examples of explicitly stated curves. And there's two examples of implicitly stated curves. So I think the difference is obvious. I think just these examples fairly clearly demonstrate what explicit means and what implicit means. But what do you think? What's the difference? Here's another one. Yeah, exactly. So explicit means it says y, or it doesn't have to be y, obviously it could be any variable, but y equals the equation. That's an explicitly stated curve or line. They don't have, and it's not necessarily function. What's something that's interesting today is not everything we're going to work with will be a function. Okay, when a curve is implicitly stated, it's not solved in terms of a particular variable. Okay, the variables are like mixed up and muddled on the same side, or however you want to think about it or describe it. Sometimes you have a curve or a line that happens to be implicitly stated, but it could be explicitly stated. Like these two, I could rearrange them to y equals negative x plus 5. Or in the case of the second one, I think it would be y equals negative 3 over 4x minus 3. Right? So I've solved those and now they are explicitly stated, whereas before they were implicitly stated. So you can sometimes switch back and forth between them. If you had a question that was asking you to take the derivative and it was implicitly stated, but you could rearrange first and differentiate the way we've been doing, then go for it, unless it says use implicit differentiation or something, right? But like if you may have a choice in some cases, you'll see that when you take the derivative with implicit differentiation, it's a bit trickier. Like it's a bit different. It's got a couple of extra things to watch out for. So if you could rearrange and isolate, that might be something you would choose to do. In some cases, it's a good idea. In some cases, it might not be. Okay? And I think there's one question in the practice where I think it's a challenge question, actually, but it asks you to do both and sort of decide which one's easier, which one's harder. Usually, if you could rearrange, it's probably going to be kind of easy no matter what, but not always. Does that make sense? That's the first thing that we need to know, is that today what we're talking about is curves like these. Does anybody recognize this particular one right here? Anybody know what that is? It's a circle, exactly. That's right. It's a circle. And what's interesting about the circle, we don't do it a lot, but we do talk about it in grade 10, and it pops up just a little bit here and there. And when you get just x squared plus y squared equals, in this case, 25, it's a circle with a radius of 25, and it has the center of the circle, in this case, is at 0, 0. Okay, so it would look something like this, where I would go 5, 5, -5, -5, the radius of 5. If I meant to rearrange this first, doesn't matter. The trick is, if I graphed this, I would only actually get the top half of the circle. So in this case, I would be doing plus or minus. So that would be a weird way of writing the equation of a circle with a plus minus in it. You could. We would understand it. But circles are more commonly written like that. As an aside, if it was x plus 2 squared plus y minus 5 squared equals 25, these would be horizontal and vertical shifts. That would change the center of the circle. And then if I had a multiplier on the outside, that would stretch it, so that would turn it into like an oval, or we actually call it an ellipse. I think I have an example of one here. So there's an ellipse, because this one is, I multiplied by 3 or something, or I multiplied by 2, I think, something like that. But anyway, okay? But that's not something we need to really worry about right now. And we saw this on Friday. Technically, when we're taking derivatives, we didn't know this up until Friday, but you're taking it with respect to a particular variable. So we usually take the derivative with respect to x, and that gives us dy by dx. It's clear when you've got an explicitly stated function that the input variable, usually it's been x for us, is the thing on the one side of the equation, right? So that's what you're going to take the derivative with respect to, like all these ones at the top here. We took it for granted that it was always dy by dx. We saw a couple of examples with s and t, so then it would be ds by dt. Like we did see that a little bit. If it was an application, you would have that. Otherwise, it's usually x. But if it's implicitly stated, maybe it's not as obvious, because you got two variables. Has everybody got that okay? But you'll see when we look at the instructions, it says find dy by dx. So I mean, it's telling you which variable to take the derivative with respect to in the question. And that's not something that we change up. Like, we're not going to trick you and say find dx by dy or something like that. At least we never have done that, or I never have. Okay, but I guess it's good to be aware that we are kind of taking for granted that we're always doing it with respect to x, but you could do it with respect to any variable. All right, so let's see what this looks like. This is the same circle that we just saw. The rules don't change for the parts that are the same as they always have. It's not like all of a sudden we do something different. The derivative of x squared is still 2x. The question is, what's the derivative of y squared? But all the rules apply. All the rules that we've been using, quotient rule, product rule, power of a function rule, all those are still true. It's just, how do we apply them when I'm taking the derivative of y, but it's with respect to x? Anybody have any thoughts? You remember from Friday, we did kind of talk about this. So I would start with, it's kind of like power of a function rule, where y is the function. So I bring the exponent down out front, multiply, leave the function alone, subtract 1 from the exponent, so 2y to the 1, but then I have to multiply by the derivative of what's inside. So what is the derivative of y? Good. That from Friday, this is what we talked about. With respect to x, this is a bit of a strange thing because we were taking it for granted that it was notation, but the derivative is dy by dx. So that part is required. And that's really the kicker from today, right? Like that's the thing that we need to be mindful of is whenever you're taking derivative of y, and there's a couple of like cases that come up a lot that you got to watch out for, but that's it right there. Okay, you got to remember to do that. I'll remind you, technically speaking, there's a dx by dx whenever we take the derivative of x with respect to x, but we don't have to write it, but it is there. And then this is just going to be equal to 0 because the derivative of 25 is 0. Any questions about that? Now, it says find dy by dx. We haven't done that yet. We've only taken the derivative. So what do we have to do? Rearrange and isolate for dy by dx. So I'm going to move the 2x to the other side. Then divide both sides by 2y. Uh-oh. Crash. There we go. By 2y. And then I'm just going to simplify, get rid of the 2's. You wouldn't have to do that in 2 steps, obviously, but there we go. Now we have it done. So that's pretty much guaranteed. You're always going to have to do that. Isolate for dy by dx. The question says leave an implicit form, and I think all the examples we're going to do today are going to look like that, but throughout the course they won't always. Sometimes, like I said, you could, like this one you can't isolate nicely for y. You would get a plus minus. But sometimes you can isolate for y. And if I could isolate for y, I could take y and sub it in for y. If it was like y equals 6x plus 3, I would take that and sub it in for y and get an expression just in terms of x. So that is something that will happen here or there, more later in the course. Most of what we're doing right now is leaving an implicit form, in other words, leaving both x and y in there. No, it's y to the 1. Yeah, I was worried about that. I'll change it to a 1. I was wondering if somebody was going to think that. Right? Subtract 1 from the exponent. Yeah. Okay, any other questions? So that one's done. There's a little question here. Why does the derivative have both x and y in it? It's a bit of a strange question maybe because, like, well, that's how the algebra worked out. What do you mean? What kind of a question is that? But I want you to think about what the derivative is, what it does, how we've used it, and see if we can think about that in a different context. What do you think? What are some of the questions that we've been asked to do with the derivative? Anybody have an idea?
It has x and y because the slope, like along any point of the circle, like it has to have both x and y.
So one of the things that we ask you to do is find the slope when, I don't know, x equals 2, right? So what if I ask you to find the slope when x equals 2? Well, that's not explicitly defined. That's not clear. That 2 or that 2, the slopes are different. So when you're, and we're going to do this today, when you're asked to find or solve a problem, you need to know why, because you need to know which of these points you're actually talking about, you're finding the slope of, they're going to be different. So it makes sense, like algebraically it makes sense, graphically it makes sense, but conceptually, hopefully, it makes sense that the derivative in this case would have to have a y in it so that we could determine which of those 2 points we're finding the slope of. Okay. This one's pretty straightforward. If you want to give it a try, you can. Gesundheit.
Thank you.
So again, the same rules apply, right? 2y squared, I bring the exponent down, multiply it by the coefficient, subtract 1 from the exponent, but don't forget the dy by dx. And isolate for dy by dx. You would not have to, but in this case, if you wanted to pull that negative out, and then I'm applying it to the top, so the top are trading signs, and the bottom's not positive. A little bit of a more natural way of writing it, but you certainly wouldn't have to do that. Seems easy enough, right? Not too bad. Don't forget the dy by dx, and there's a little bit of extra work when you have to rearrange. Questions? So this one probably looks just as straightforward, but it's actually not. There's quite a significant trick to it. Something that is so small and subtle that even though we're talking about it today, and a lot of the questions have this in it, it's easy to miss. Really, really easy to forget and make this mistake. What's different about this question compared to the last two?
X and Y are together.
Yeah, x and y are together multiplied in the same term. So why does that so significant? Why does that matter? What do we have to do? Well, it's going to impact the derivative. Yeah, I mean every function has a different derivative, but there is no. You could on occasion factor it. I don't think that would be helpful in this case. You'll end up kind of in the same position. Remember? Yeah, maybe, but if I did that, don't write this down. What do I get? Like, what does this look like? I don't know. That's easier. I don't know. That looks like product rule, doesn't it? So maybe that even complicated matters a little bit more. In the end, it would probably be about the same level. But here's the trick. This is also product rule. X times y is multiplying two things that you're taking the derivative of. So this right here is product rule. And that is something that people miss even though we talk about it. Something as simple as x times y, even not y squared or anything like that, just x times y is product rule. So be very, very careful of that. How do you apply it in this case? So the derivative, so there's the first part and the second part, right? Derivative of the first part is just 2 times the second part, which is y squared, plus derivative of the second part, which is 2y dy by dx times the first part. So I'm going to write this out, and just for our note, again, normally we probably wouldn't do this, but product rule, where my p is 2x and my q is y squared. So p prime is 2 and q prime is 2y dy by dx. If I change the colors, then it kind of highlights it a little bit better. Okay, equal to, oh, I'm not done yet. That was just the derivative of the first part. Again, this is a little bit curious. It's never really happened before, but this looks like 2 terms up here. But when I take the derivative, I'm going to have more terms. Because of product rule, it's this plus this. I end up with more terms. So this is plus 3y squared dy by dx equal to 0. So it's easy to miss a term or lose track somewhere because we have more terms in the derivative than we started with. Okay, and how am I going to isolate for dy by dx in this case? Yeah, I'm going to get everything. I'm going to chuck stuff to the other side and then factor out dy by dx and then divide. So this is going to, and I'm going to simplify a little bit here. This ends up being 4xy dy by dx plus 3y squared dy by dx equals negative 2y squared. Okay? Any questions? So that's like a very typical implicit differentiation kind of question. Got a little bit of hidden product rule, a little bit of algebra to simplify it in the end. That's, to me, is kind of what it looks like, right? You could, but it would be like, you know, why would you or would you? I mean, in this case, yeah, because you have a y on top, would factor with the 2 on the bottom. You might or you might not, depending on what you're doing. Yeah. 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 We don't usually mix and match those two, but yeah. Okay. So the derivative of 1 is 0. So again, product rule. Derivative of the first part times the second plus the derivative of the second, which is 4y cubed times dy by dx, times the first part, which is negative 3x squared. And then the derivative on the other side, oh, geez, what's going on today? Very strange. Oh. What's the derivative of root 2y? Do you have a question? Say that again? To an exponent of 4 or something? Oh, here, no, because I didn't take the derivative of this part. This was the derivative of this. There's my first part. There's my second part. So the derivative of this times just y to the 4. Didn't take the derivative of y, so I wouldn't in that case. So this is like, people sometimes get confused when it's a root 2 or something like that. It's just a number. What's the derivative of 2x? It's 2. So what's the derivative of 2y? Whoops. It's 2 dy by dx. So the derivative of root 2y is going to be root 2 dy by dx. So just something, I guess, to be mindful of. Sometimes people overcomplicate that and forget root 2 is just a number. Okay, and then we're going to do some work to simplify this. Getting all the dy by dx terms on one side and then factoring. Okay, any questions? All right, now, what does it look like when you're actually answering a question with implicit differentiation? Find the equation of the normal line to the curve y to the 5 plus x squared y minus 2x squared equals negative 3 at the point 2, 1. Oh, by the way, I forgot to do this. As you're writing that down, some of these curves are pretty interesting. So we talked about the circle. That was the first sort of example, I think, or the second example, B. That's what it looks like. That's one whole relation. So not a function. A lot of these will not be functions. Some of them are, but a lot of them are not. So they can't be written explicitly in a nice way. But strange, eh? It's got this little blip over here, and then it's got all those parts. The next one that we're looking at looks like this. This is what this one looks like. Looks like it is a function. I can't say that for sure because I can't see the whole thing, but to me it looks like it probably is a function, this one. Okay. Oops. What is a normal line? There was a question on one of the days that was like an extra sort of challenging question. And it's not really all that challenging, but except that I hadn't taught you what a normal is yet, so you had to go figure it out for yourself. Did anybody look it up? What's a normal?
Is it like the line that's like perpendicular to the tangent?
Yeah, exactly. So if I have the point 2, 1, let's say this is 2, 1. Here's the tangent. The normal would go through the same point, but it's perpendicular to the tangent. Turns out this is a really important definition that we'll talk a lot about in vectors when we talk about vectors in this course. Okay, a normal is a very, very useful property of a vector. Anyway, now it's something that we know. It's a simple definition. It doesn't change the question all that much. It's pretty straightforward. There's one extra little step. Otherwise, finding the equation of a normal line or the slope of a normal line is something that we already have all the skills to do. So first thing we're going to do, so to find the equation of a line, just to recap from before, we need a point, which we already have, and then we need the slope. How are we going to find the slope of the normal? Find the slope of the tangent, and then get the perpendicular slope from that. How do we get a slope of a tangent? Take the derivative, sub it and solve. So we'll take the derivative of this. Again, be careful. This is product rule, x squared times y. See, it's hidden. Like, it's really easy to forget that this is product rule. And I guess people would just take the derivative as separate parts. So the derivative of the first thing is 2x times the second thing, which is y, plus the derivative by dx times the first thing, which is x squared, minus 4x equals 0. Now I got to do some work to isolate dy by dx. And this is what I was talking about before. It's interesting that this expression is still implicitly stated. It's got x and y in it. Now, in this case, we're given both x and y. X is 2 and y is 1. If you were just given x, you'd have to sub in and solve for y and find y, because we need both of them. So this might not be an equation that you could sub in for x and solve for y. That might be tricky, right? But if we gave you a question like that, it would be one that you could. So now we're going to do dy by dx at 2, 1, or x equals 2, y equals 1. You don't have to write it both ways, but that's what we're doing. So 4 times 2 minus 2 times 2 times 1. 5 times 1 to the 4th plus 2 squared. That looks like 8 minus 4, which is 4, over 5 plus 4, which is 9. So the one extra step when you're doing this, I mean, obviously taking the derivative is different because it's implicit, but the ideas are the same. That is the slope of the tangent. So what is the slope of the normal? It's a perpendicular slope, which is, right, negative reciprocal. So flip the sign and flip the fraction. Don't forget to flip the sign. Everybody okay with that? And then, and I said this the other day, don't forget, like, go back and read the question. Some people might get that far and think they're done, but we're not done because we're supposed to find the equation. So at 2, 1 with the slope of negative 9 over 4. Multiply both sides by 4. I don't think it said to put it in standard form, but that's always what we do. So that's what we're going to do. Minus 9x plus 18. So multiply by to clear out the denominators. Multiply through by the 9. And then bring everything to one side. That's what one of the mistakes on the quiz was, people forgot to clear the fractions. So watch for that. Any questions about that one? We're going to do one more. And again, it's not really different. It's going to be very similar, except for taking the derivative part, which is a little bit different. But otherwise, nothing really new here. It's a bit unfamiliar the way this one's going to work out. But overall, not some of the harder stuff that we do in this unit or in this course. Find the points at which the slope of the tangent to the given curve is 1. So remember, when we did this problem solving day, we talked about 3 different types of questions. Find the slope. That's the basic, straightforward one. We've done that a ton already. Find the equation. That's the one we just did. Find the points given slope is the third type, and that's obviously what this one is. So the slope of the tangent to the given curve is 1. What that's telling us is dy by dx is 1. So when I find dy by dx, I can sub 1 in for it and solve for whatever's left. So 3y squared dy by dx equals 3. Derivative of 3x plus 5 is just 3. Three over 3y squared and you end up with dy by dx equals 1 over y squared. So interestingly, this one doesn't have an x in it. Just how it worked out. This is why it can be a little bit unfamiliar, these types. Everybody okay so far? Pretty straightforward, right? So remember we said the slope is 1, which means dy by dx is 1, which means 1 equals 1 over y squared. Multiply both sides by y squared. I get y squared equals 1. What do I do next? Take the square root. What do we have to remember when we take the square root? Plus or minus. That's where some people would make a mistake. So when y is plus or minus 1, it said find the points for a point that needs the x value and the y value. So almost always we find x first and then we have to go and use it to find y. But interestingly, in this case, we found y first and we have to use it to go find x. Right? So find x at y equals plus minus 1. So y equals negative 1. And this is where we go back into the original equation. So I'm going to subtract 5 and divide by 3, which looks like negative 2. Same thing. That one looks like negative 4 over 3. So the 2 points are negative 1, negative 2, and negative 4 over 3 and 1. So like, pretty easy. I mean, there's nothing really hard there, but just a little bit different, a little bit unfamiliar. Yeah.
So can we just say that's like the cube root of the 3x plus 5?
That's right. You could solve this one for cube root. Yeah.
So that's one that we can do like calculate.
You could. Other questions? Say that again. I wrote it backwards. Whoops. Thank you. Yeah. See what happens, I guess? We're so used to having x first.